linear time. Okay. Right. So let's go back here to our class, and let me share the screen here. Share the screen. Where is this? Share screen. Right. So share this. Okay. Right. So this was our setup. Let me see. Okay. So this was our problem. How to find the longest common substring of two strings. Okay. So in this example here, we have two strings, like string 1 and string 2, and the substring alive, okay, is common, right? So it's common to both strings. It's a substring that exists on both, and actually it's the longest, right? So the largest one. So we have an idea for a non-naive algorithm, okay? But actually this algorithm won't be non-naive, it will actually be similar to the naive one, okay? And our idea was we basically take our string S2, okay? We try to read it in the suffix tree of the string S1, okay? And if at some point the letter that we're reading fails, we have to restart at the root, okay? So restarting at the root actually is bad because it basically means that we have to reread almost the whole string, right? So it's still going to be quadratic, right? So let's do that analysis. Okay, so today is 7th of March of 2021. April. Okay. All right. So let's consider an example where this bad case might actually occur, right? So we need a string 1 and a string 2, right? So what I'm going to do is I'm just going to use some x's, right? So, and use a bunch of a's. Okay, so like 4 a's, and then an x, then another 4 a's, and then an x, right? So now suppose that my string S2 is basically just a's, right? Okay, but we have 5 of them, right? So if this is our example, what would our algorithm do, right? So we basically have here the suffix tree for S1, right? So we have the suffix tree for S1. Actually, it's probably best the other way around. Let me do this the other way around. Okay, so let me just put an A here. Okay, so this would be too easy, but let me just put an X here. Right, so, okay. So what would we do? So basically, we would try to read string S2 in this suffix tree, right? So I'm not drawing the suffix tree, but basically what happens is that, okay, drawing suffix trees is a bit hard because if we draw them like this, okay, this one is actually incomplete, right? So this one is incomplete. Right, so basically this one is incomplete. Okay, this one is actually the one here that I showed you in the definition. This is a complete suffix tree, right? So this one is actually a complete suffix tree, right? Can you guys hear me okay? Because I swapped internet to IST today, so I'm not sure if I'm having lags on the network or not.
It's fine.
Okay, thanks. Okay. Right. So basically, we would read these 4 letters. I'm able to read these 4 letters, right? So the 4 A's, I'm able to read them. But then I get an X, right? And there is no X over here, right? So if I look at the suffix tree here for this string, it should have an A, okay? And actually the suffix tree for this string is pretty easy to draw. I'll actually draw it explicitly because it's actually a good exercise. So let's do that. Okay, so the suffix tree for the string that I dropped there is actually pretty easy. You just have the roots. So this is for S1. So just have the root, you have all of your A's, and it's going to look like this. You have an A, then you have a node, then you have an A, then you have a node, then you have an A, then you have a node, okay, and an A. Okay, so here's 4 of them, okay, and then A, and then node, and so on. And because you have the $sign over there, so the suffix tree is explicit, that means that everywhere here you've got dollars. And this is actually the suffix tree for this string. Okay, I'm not writing the bijection between the leaves and the suffixes, but you can figure it out. So this is actually the suffix tree for this string S1, right? Okay, it's incomplete because I didn't draw this last part, but that's fine. All right, so what happens here? So I try to read these A's. Okay, so I get to read these 4 A's, right? So I go down, 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 right? And then I try to read the X, and I cannot read an X here, right? Because I either have an A or a $, and neither of these match the X that I want to read over there, right? So everybody got the problem? So according to our semi-naive algorithm here, so we're trying not to be naive, but we're actually being naive because it says that if at some point the letter fails, then we restart at the root. So what restart means is not completely clear, right? So what should restart mean? Okay, so basically restart should mean I start again, but instead of starting at the first A, I start at the second A, okay? Because it may be that the longest common substring actually started in the second A. In this case, it doesn't, right? But it could be like, so imagine, for example, my string could start by a Y, and if my string started by Y, and if I tried to match Y, I wouldn't be able to match Y, and therefore, actually my longest common substring would start in the next position, right? So because of that, I have to test basically all suffixes. And if I have to test all suffixes, that means that on the second time, I am going to start here, right? So I'm going to start at this A, right? I'm going to try to match these 3. And I actually am able to do that, right? But the problem is that I'm basically rematching over here. So everybody got the problem here?
Yes.
Right, so in this example, so we can basically generalize this example. So we can think what's the time to find the longest common substring in this family of strings. Okay, so basically you have a bunch of A's. So suppose you have, okay, let's suppose I have n A's and then a $, and then for my pattern, I have basically m A's and then an X, right? Sorry, this is S2. Right, so if I have this like that, it basically means that every single letter is matched a bunch of times, right? So in the first time I match all the A's, okay? In the second time I match all the A's -1, and then I match all the A's -1, -2. So basically the time for this algorithm is, okay, so first I match all the A's, right? Then all the A's -1, okay? And then all the A's -2, okay? And so on and so forth. Okay, and until I match only one A or one X and so on. So basically the idea is that this is actually O of M squared, right? So actually here I was being a bit too pessimistic. Yeah, but this pessimism is okay because I actually didn't say which one of the two was the largest one. So that's okay. So here we've got O of M squared time, right?
Sorry, one question. But you also have the time to make the tree, right?
So yeah. Just ignore the time to make the tree. Yeah, that's a very good question. But the time to make the tree is the subject of the next classes. Okay, so we're going to see the algorithm for making the tree. But actually, for the algorithm to make the tree, we need the piece of structure that we're going to invent right now. Okay, but that's actually a good point, right? So, but the time to make the tree, okay, so I'll put here. Okay, so plus the time to build the tree. But we are going to be able to build the trees in linear time, okay? To build the suffix tree of S1, okay? But this is going to be O(n), right? So this is going to be linear, okay? But this is the stuff that we're going to see in the next classes, right? So yeah, so the bound that I had above was actually pretty straightforward because it was pessimistic, but actually included this time. So this is chapter 6. Okay, so this is the whole of chapter 6, and we are getting to it. It's a bit weird that we're starting with the application. So basically, this application is on chapter 7, but it allows us to discover a fundamental structure that suffix trees need to have. Okay. So what's the problem right here, right? Okay, so basically the idea is that, okay, suppose that you have your S2 suppose you have your S2, right? So this is your second string. So at some point, there is some letter, okay, so I'll just call that letter C, okay? And then there is some string, alpha, okay? And then there is some other stuff here. Let's assume that I have some X, right? Something like that. Right, so what's happening in this algorithm? Okay, so what's happening is that here you have the suffix tree of S1. Okay, so you have this suffix tree. Sorry. Suffix tree of S1, right? So you have this suffix tree over here. Okay. Let's assume that I was able, okay, so at some point in this algorithm, I was able to read C alpha on my suffix tree, but not X. Okay, so I was able to read C alpha, and okay, let's assume I reached the node. Okay, I might not have reached the node, but let's assume I reached the node because it's going to make our life much easier. And here in this example, it's always true, right? So let's assume I reached the node, but now let's assume that if I look at all the letters here, all the letters that start here, they're all different from X. Okay, so this is different from X, this is different from X, and this is different from X, right? So all the letters here that leave from alpha, they're all different from X. That means that I was able to read C alpha, okay? But then I'm not able to read X. Is this setup clear? Yes?
Yes.
No? Okay. Okay, so I don't know how many children this node has, but at least it needs to have 2, right? It needs to have at least 2 children, right? Okay, so what our restarting algorithm is doing is the following. So basically, I'll go again to the root, and I'll start at the root and search for alpha, basically. Okay. And now, if this thing over here is a node, right? So if this thing over here is a node, that means that there must be a node over here. Why? Because, okay, so if I have C alpha A and C alpha B, that means that C alpha A and C alpha B must occur somewhere in S1, right? So that means this. Okay, that means that if we're in this situation, that means that S1 is something like this. It has C alpha and then an A, okay? And somewhere else it has C alpha and then a B. Okay, alpha is not a letter, it's a substring, okay? Okay, so for some substring, but okay, so for some substring alpha, okay? Right, so if I have this node over here, if I have a node, that means that I need to have C alpha A and I have to have C alpha B. But if I have C alpha A and I have C alpha B, in particular, I have alpha A and alpha B, right? And if I have alpha A and alpha B, that means that there's got to be a node over here. And our conditions are that A is different from B, and A is different from X, and B is also different from X, right? So these are the 3 conditions that we have here. So it's our hypothesis. Okay, so here it's an hypothesis, and here that means that that is also a node, right? So everybody got this logic? So basically what I'm saying is that if I have a node with a path label C alpha, okay, then I have to have a node with a path label just alpha. Okay, so that's our reasoning over here. Okay. Okay, so that's our logic. Okay, so this is an observation. If there is a node with path label C alpha, okay, so this is like C dot alpha because it's concatenated, then there is also a node with path label just alpha. Okay. Okay. This is basically an internal node, so it's basically not a leaf internal. Okay, so there's also an internal node, right? Okay. So what our algorithm is doing is it's reading C alpha in the tree, and then it's reading alpha. And this is the reason why it takes so long, right? Because it's rereading alpha, okay? So the problem with the time complexity of the previous algorithm is that it is rereading alpha, or okay, never mind. In the ST of S1, right? So this is the problem with the previous algorithms. So anybody's got an idea how we can fix this?
You can just skip alpha, and so when we restart reading the word, you start with X.
But to skip alpha, I need to do something. What do I need to do?
Know how long alpha is, so you can skip it.
Okay, it's not just how big alpha is, because I need to find the position in the tree where I should go to, right? So how do I find that position?
Can't you can go back to the root?
Yeah, but right? If I go back to the root, I have to reread alpha to find the position. So the thing is, I'm here at this node, and I want to go there to that node, right? But if I start from the root, I either can read C alpha or I can read alpha. But I want to go directly. What should I do?
Professor, could you say the problem again?
Right. So the problem is we have this algorithm over here, right? So this one that's finding the longest, I'm trying to find the longest common substring, right? So what I'm doing is I build a suffix tree for S1, okay? And then I read every suffix of S2 in that suffix tree, right? That means that I'm basically rereading substrings, right? So a more specific case is that if my S2 looks like this, it has a C somewhere, then it has an alpha, which is a big string, and then it has an X. So if I do this, if I start from the root, I read C, and then I read alpha, but remember that alpha can be big. And then eventually, I'm not able to read X, okay? Because here the letters are A and B, and they're different from X. So what my sort of naive algorithm is doing is restarting. So restarting means that I go back to the root, and again, I read alpha to reach that node over there, okay? So the problem is that this takes too long. I should be able, I'm trying to skip this computation. So what should I do to skip this computation? Can I skip it or not?
Thank you, Professor.
Yeah, you're welcome. Okay, so ideas?
What Oscar is saying is that you found a substring C alpha, and then X doesn't work. You don't need to check alpha because X will not work as well, so you'll find the
yeah, great question. Great. That's why I ask questions. It might work, right? So there's no saying that it's not possible to go by X over there, right? I want to go to that node because that node might have more children, and that's actually very possible. That just means that somewhere here on this string S1, something like this should appear. And then it could be actually
without the C, right?
That's over here. Like here you could have like a big beta, right? Without the C, thank you. Without the C, right? So something like this may occur. I could have alpha, B, and then a beta, right? And this beta is actually also over there in string S2, right? So that's a very good point. So why do I want to go to that node? If going to that node means that I won't find the longest substring. The thing is that I might find a longer substring. So I really have to go there.
Okay, thank you. Just the substring, it's alpha X beta, no?
Alpha X beta X, sorry. Let's put here alpha X beta, right? So this might occur here. So there might be an alpha X beta somewhere in S1. And that means that it will show up here in the tree. And that means that I cannot skip going to this second node here. So I really have to go to that node and try to see if I can extend it further. So I really have to go to the node. But what I'm trying to do is to go there faster. So what can I do? Ideas?
Can we somehow use the depth of the tree because it has to be -1 from where we are now?
right. Even if you go to depth d-1, there might be a lot of nodes there. Like I can't actually go and scan the nodes or something like that.
Oh, okay.
Can you guys hear me? Yeah.
Can we have a pointer from one node to the other?
Yes, a pointer. Thanks. That's exactly it. So let's assume that I have this pointer. Okay. Okay. So this pointer has a very specific name. It's called the suffix link. Okay. Let's assume. Okay. Let us assume that every node, okay, so it's basically internal node. For the leaves, you can also define this, but it's kind of straightforward. Okay, so I'll put every node. Okay, so every node of the suffix tree. Suffix tree. Not try. Suffix tree stores a suffix link. So this is called the suffix link, right? Right, which is a pointer from the nodes with path label C alpha, right, to the nodes with path label alpha, right? So that's the definition of suffix link. So now that we have the definition, let's store them here, right? So here in our example, so what's the suffix link of this node over here?
It just goes up.
It just goes up, right? It's like a parent pointer. In this specific tree, suffix links are like parent pointers, right? But in general, suffix links are different. But here they're like parent pointers, right? So here the suffix link from this one is going there, and this one is going there. So there's only one suffix link, right? So the suffix links, they only point to one place, right? So they only point to one other node. And this observation here actually is crucial because it means that the definition of suffix link is actually sound, right? Because I cannot store a pointer if there was no node over there, right? So this observation was important because it tells us that our suffix link is well defined, right? So for each node, there is always a suffix link, right? So each node has always a suffix link. Okay, so all of these nodes have suffix links. Okay, you can also define them for the leaves, and for the leaves it would be something like this. We usually just define them for the internal nodes. Okay, so here I said every internal node has a suffix link. Okay, so this basically means that every node. Okay, so here it doesn't say that this definition doesn't apply for the root. Okay, but we can use a sentinel. Okay, we can use a sentinel node, right? So the previous. Okay, so for every node except the root. Okay, so the root doesn't need to have a suffix link, right? Because there is no letter that I can remove from an empty string, right? Because the path label of the root is an empty string. Okay, so this definition doesn't define a suffix link for the roots. For the roots, okay, for the roots, we can store the suffix link for a sentinel node. Okay,
Professor.
Yeah.
What if we had a pet label like another pet label like beta alpha? What would be the
Right.
imagine if we have three: C alpha, alpha, and beta alpha. What would be the suffix?
No. Alpha is a string, right? So
yes.
So
but
I'll write this in the definition. So alpha is any string and C is any character, right? So here I'm using them as mute variables. They're quantified, but I'll write that to make it clear. Let's assume that every node of system with a palette label CL. Okay. Okay, so I'll write it here where C is the letter and alpha could actually be an empty string. Okay, so it could be an alpha is just a substring. The substring. You could I can just call it a string. So it's just a string, right? So alpha can have several letters. C is just one letter, so you need to have one letter, and alpha is a bunch of letters together. Is that okay?
Yes, but my point was if we had another case, so a case where there are three substrings, one that is C alpha, another alpha, and another beta alpha, that a beta is a different character than C, what would be the shortcuts for that? So we are linking C alpha to
we have
alpha.
C alpha here, right?
Yes.
So where is your node?
No, so my point was
beta here.
No. My point was to another two substrings coming from the root, and how could we create?
What do you mean? If there's an alpha here and there's also a beta?
Beta alpha, yeah.
Alpha?
Yes. How could we create a shortcut between these three cases?
No, but so imagine there's a node here, right?
Yes.
So that means there is a node here. Okay. So basically the suffix link goes from here to there. Is that it?
Yes, but in the case of beta alpha, what could...
No, beta alpha is potentially different, right? So if beta is different from alpha, that's okay. Sorry, if it's different.
Okay.
Right, so there might be other structure in the tree, right? But this definition is for every node. So basically the idea of a suffix link is that you take the path label and you remove the first letter. That's all it does. So you just discard the first letter. Is that okay?
Yes.
Let's okay. Let me just finish here. For the root, we store a suffix link to a sentinel node. Basically, what I mean with that is that I'm assuming I have a suffix link here, right? So these are suffix links, right? So all of these are suffix links. So I assume there is some other special node, which actually doesn't matter what it is. And then you can go from that node back to the root, and you can do that with any letter. Okay, so you can go back from the sentinel. Okay, so this is the sentinel. Okay, and you can go back to the root with any letter. Okay, so any letter will take you from the sentinel back to the root, right? So this stops being a tree, but it's actually pretty good for our code. But let's ignore that for a moment and let's go back to our original suffix tree. So remember the suffix tree that we drew over here, right? So here's the suffix tree that we actually drew completely, right? So this is actually a complete suffix tree, right? So there is only one internal node, okay? So for the leaves, you can also define suffix links, but it's mainly interesting for internal nodes. So the question is, what's the suffix link of this node over here? Where should I point my suffix link here?
To the other internal node.
Yeah, to the other one, right? Okay, so this is the suffix link here. Okay, in this case, my X is C and my A is alpha, right? So the idea of suffix link is just that you read the whole path, right? And you remove the first letter. And likewise, if you want the suffix link from this node, it's actually back to the root, right? So that's our suffix links.
I have a question.
Yeah.
In practice, will there even be both of those daughter branches for the nodes that are connected by a suffix link?
Yes, because of this question over here, right? We can build this string, right? So this that we use for S2, okay? So
okay, they can have different.
They can have difference, right?
Okay.
So we can actually build these. We can actually build a concrete string from here. Like suppose that you really imagine the string C. Okay, so for alpha, I'm just going to use a T, CAT, CTA, right? CTB, and TX, and then this could be actually a B, something like that, right? So if you try to build the suffix tree for this string, you'll notice that there will actually be 3 internal nodes, and two of them point to the same one, right? Okay, yeah. This is a good exercise. We can then do this in the lab or something like that. Okay.
Yeah, I got it. Thanks.
Right. Right. All right. So now if we have suffix links, that means that instead of starting at the root, we can simply use the suffix link that is stored on the tree, right? So here in this example, right? So I would go. So initially, I would start reading the 4A's. So I'm able to read the 4A's, right? So I get to this node over here, and then I cannot read the X. So instead of restarting at the root, I just use a suffix link and go here, okay? And again, I try to read the X, okay? And this time it fails again. So I follow another suffix link and I try again, and so on and so forth, okay? This is a bit tricky because life was a bit easier in this example because our point, the point that we're keeping track, was actually aligned with the node, right? So when we descended with our string, we always hit the point node, okay? And because we're storing suffix links in nodes, this is possible. But if you are in a general point, right? So suppose like over here. So if you're in a general point, things can get trickier, right? So suppose that instead of being here at this point, okay, suppose that I'm actually over here, right? Suppose that I'm in this point, right? So suppose that I was reading my string and it was XABX. Now I want to use a suffix link from here, okay? And I can't because there isn't a suffix link. So what I should do in this case is I should go to the parent, okay? Use the suffix link from the parent and then go down, right? So from here, I want to go here, okay? In this case, this was constant, but in general, it isn't, okay? And we're going to see a general technique for that, right? Sorry. But for now, let's just rewrite give a pseudocode for the algorithm that we have so far, okay? So this process of going from this point over here to that point over there, right? So this process from going from here to there, I'm going to call this a suffix jump because it actually isn't exactly a suffix link, Okay, so it's a suffix link, but it's a bit more than a suffix link. Okay, and it has an important trick associated with it. Okay. All right, so, oops, what happened? No, okay. All right, so our pseudocode so far is the following. Okay, so our pseudocode so far is the following. So we start with some point P, okay, and the point starts being the root. Okay. So I'll wait. Okay, so we start with the root. So now we basically just run a for cycle, right? Something like this. So we run our indexes, and now we need to have some indexes over our string S2, right? So let's suppose I start at 0, okay, and I go while it's smaller than the size of S2, right? So we're using S2 in the tree. And then basically I just do I++, right? So this is okay. Now what do I need to check? So so again, we're going to have this sort of amortized cycle thingies, right? So we need to check. While it's not possible, okay, so not descend from P with letter S2I. Okay, so what am I doing here? So I'm checking if I can descend using the letter that I'm trying to read. Like, so in this example over here, where I had a bunch of A's and an X. So when I reach the X, I'm trying to descend by X. And I'm not able to descend by X. So what happens is that I use the suffix link, and I use the suffix link, and I use the suffix link, and so on, right? So I might need to use suffix links a lot of times, right? So while I'm not able to descend by X, I basically replace P, okay? Not by the suffix link, but by the suffix jump, right? Jump from P, right? Okay, so okay, so if I'm not able to descend, I'll go up and up and up and up, right? Eventually, if I'm way too up, I'm going to reach the root, okay? And if I reach the root, then I should be able to descend by the letter. But it could be actually that something really strange happens, which is the letter actually occurs in S2, but it doesn't occur in S1. In that case, that loop is still good because we added this sentinel node, which means that instead of ending up at the root, I'll actually end up in this sentinel. And then it's possible to descend, okay? So, okay, so this actually is, sorry, this actually is, this is a query, okay? I'll just write everything here. This is a query. I'm just checking if I can descend, okay? And if I'm able to descend, I will descend, okay? Okay, so descend is just go down, right? Or read, we've been calling this read. Okay, so from this point, and you just read this letter, right? And that's basically, this is our algorithm so far, right? So I just need to fill in the details, right? So where? Okay, descend queue, right? Right, with some point and some letter, right? Returns true. Okay, so returns true. True if it is possible to read letter C below the point P, right? So descend Q just returns true if it's possible to read.
Professor,
yeah.
If that's the case, isn't that just an infinite loop?
It shouldn't be.
If you're just checking if it can descend, but you don't actually descend, it'll get stuck on that condition, right?
Yeah, but I do a suffix jump, right? So I change P, right? I change my point, right?
Oh, okay.
Right. So
right.
if I'm not able to descend, I use the suffix jump. So I go up.
Right.
Right. Okay. So what else? So we have descend Q. Okay. So descend actually changes the point, right? So descend PC changes changes. Okay, actually it doesn't change the point because I reassigned it, but okay. Returns. Sorry. Returns the point with the same path level as P, but with C appended at the end. At the end, right? So basically, just go down by C, right? So the only thing here is the suffix jump. So the suffix jump is a bit tricky, right? Suffix jump. So suffix jump is complicated. Okay, so what is suffix jump? So if P is a node, then suffix jump is the suffix link of P. Right? So okay, so P is your point, right? So here, so I haven't said that, but this is a point. Okay, so by being a point, it means that it could be a node, but it doesn't have to be a node, right? So it starts at the roots. What you do is, while you're not able to descend, you do this suffix jump thing, which basically means go up. And then if you're able to descend, then just descend, right? Okay, by the way, right, so let's go back here to our suffix jump thing. Right, if it's a node, then it's fine, right? Okay, if it's not a node, then it's a bit trickier, and you need to do something called the skip count trick, right? The skip count trick is here on the on Gusfield. So I'm basically going to copy the. So I'm basically going to copy the image that that's on Gusfield. Okay, so
se inscreva em nosso canal.
Okay, otherwise.
Hey Dev, seja
use
Hey Dev, seja muito
the skip count trick.
time map para cada
count.
Olá Dev.
Okay. So where is this skip count trick? This is in Gusfield.
E quando eu tô pressionando
Okay, so I'm basically just hiding a fairly tricky algorithm here. So this is in chapter
passei para a próxima fase. Tá. Nesse caso aqui, pessoal,
6.1.3.
Escorregue.
It's page 101. So
erro porque eu tô
6.1.3, page 101.
Perfeito. até botar mais caixas.
Okay, so what is it?
Aliás, vou transformar essas caixas.
Okay, so let's see what it is.
Conforme a gente já vem fazendo, né?
Okay, so in general, what happens? So in general, you have your suffix tree like over here. Okay, it has some nodes. You don't know which nodes are here, and you don't care, right? So it has some other node here and here, and right. Okay, I need some node here, right? Okay, so this is my suffix link. I'll just use my suffix link here. Right, this is my suffix link, which basically means that you have something like this. There's a letter, so we usually use C for the letter. And now my alpha is split. So you have like alpha 1 and alpha 2. Okay, and here you have alpha 1 and alpha 2 also, right? Right, so what else? But here there is more information on this. Right, so now suppose that here you do have letters, like you have A, B, C, and D, right? And suppose that you are here, that your point is actually here. So my point P is actually right over here. So that means that there could be stuff down here, which I don't really care about. Because it's above the point, so you don't care stuff that's below the point. But there could be an X and a Y and stuff like that, right? But if you have ABC here, that means that they must exist over here also, right? So, okay, let's assume that I have a T over there. I just have to have different letters, right? So T needs to be different from A, right? So the T is there. But now stuff like this might happen, right? So you might have an A, then a node, then a B. Okay, actually the B and the C could be together, and then you can have the D, right? And this could be like this, right? So your suffix tree might look like this. That just means that you have some other W there, right? So, right, so the goal is to go where? So if it's a suffix jump, right, so wait. So if I have my D, I really don't care about the stuff that's below, right? So there could be an X and a Y. There needs to be an X and Y. But, okay, so my goal is to go from here to there. So my goal is to go there. Oops. Okay, so this would be a suffix jump. Okay, or basically it would be the skip count trick. Skip count trick. Okay, so what does the skip count trick do? So in reality, how does the skip count trick work? So you just go to the parent, right? So you have your point here, you just go to the parent, right? You follow the suffix link, okay? Follow SL. And then you need to reread some letters, right? You need to read this letter, and you need to read this letter, okay? But you don't need to read the C, okay? And you do need to read the D, okay? So the skip count trick, okay? So the skip count trick, basically what it does is skips testing this letter. Okay, right, because the problem with the skip count trick would be that if you do a naive, if you didn't do the skip count trick, then this would be almost identical to our naive algorithm, right? So our naive algorithm, what it did, okay, it started from the root, but it basically reread all the letters, right? Here, that's not what we are saying, okay? Here, what we are saying is that you might need to reread some letters, okay? but it might not be all of them. Okay, so the idea is that the skip count trick is not constant, right? So if you use a suffix link, then that's a constant operation. But if you do the skip count trick, then that's not a constant operation, right? So, and that affects the complexity of this algorithm, right? So, okay, so now if we want to analyze the complexity of this algorithm, so now if we want to know how long this algorithm takes, we need to know the complexity of the suffix jump, right? Okay, this already seems very complicated because we already have 2 chain cycles. Okay, if you remember the studies that we did for amortized analysis, then you would think that, okay, even though you have 2 cycles, maybe I can prove that this is linear if I find the right potential function. But then I have another problem, is that in general, in those cases, I'm assuming that the suffix jump is like a constant time operation. And in this case, it's actually not a constant time operation, right? So the suffix jump itself uses the skip count trick, and the skip count trick is a bit, is not constant, right? So it has computation inside it, right? So it can vary, okay? So we're going to have to come up with a potential function for this and to analyze it, okay? But before we do that, let's see that this algorithm actually does what we wanted it to do, right? Okay, so what was our goal with this algorithm? So anyone remembers?
To find the biggest common substring.
Right, to find the longest common substring. And if you look at this code, I'm not doing that, right? So where is the string, right? Well, the thing is that this code is fundamental for everything, right? So it's fundamental for building suffix trees. We're going to use the same code to build suffix trees. And this is the skeleton, right? So this is the fundamental stuff. Now I'm just going to add the stuff that we need for this particular problem, right? So for this particular problem, I'm just going to try to find the size of the longest common substring. So basically, I'm just going to use some L, okay, that I can start at 0, and this is the size of the longest common substring, right? So basically over here, it's pretty easy to change this code to check, to determine the size of the longest common substring. Basically what I do is that after I descend, right, I check if the size of the current point, okay, and by size of the current point, I mean size of the path label, okay, size of path label of P, right, of the current point, right? So size of the path label of P. If this is larger than my L, then basically my L starts being this, right? And in the end, I can just return the size of the, in the end, I can just return my L, right? Okay, so this code here, right? So in the end, I can just return L, right? So I just changed the skeleton a little bit. And now it gives me the information that we wanted, right? So here, just return L. Right, so this gives us the size of the longest common substring, right? It doesn't give us the substring itself, but it's the same thing, right? So you would just, so here in this, if you actually want to store the string itself, you can actually keep a copy to the point, right? So you could keep a copy to where in the string is the longest, to where in the suffix tree is the longest common substring, right? Okay, is this more or less clear? Okay, does everybody agree that we are able to find? Okay, at least agree that this returns the longest common substring, right? The size of the longest common substring. Okay, the only thing that we have to question here is what's the time of this algorithm, right? And it's not easy, right? Because you have this for, you have one cycle, two cycles, okay, this while cycle, and then you have this suffix jump, and this suffix jump is not constant, right? Okay, but to make our lives easier, let's assume that the suffix jump is constant, and to do a first analysis. Okay, so how long does the how much time? How much time is necessary for the LCSS longest common substring algorithm? Okay, this is actually a tricky question, right? And to answer this question, let's do a first analysis, which is incomplete, where we assume that suffix jumps are in constant time, right? Okay, first analysis. Okay, so this is incomplete. So basically what we do is assume suffix jump takes 1 unit of time. Okay, we know this is not true because we know that the suffix jump is this complicated thing over here, which involves the skip count trick. Okay. One thing that I didn't say here. Is it clear for everyone why we don't need to compare the letter C? Yes, okay. Right, so the reason that we don't need to compare the letter C is the following. Whenever we're searching for a pattern in the tree, we need to compare all the letters of the pattern against the tree because we are not sure that the tree contains the pattern. But in this case, we are sure that the tree contains the pattern, right? So if the tree contains C alpha 1, alpha 2, A, B, C, D, it must contain alpha 1, alpha 2, A, B, C, D, right? Because it's a suffix tree, it contains all the suffixes, right? So if it contains one, it must contain the other suffix. And because we already know that the string we are searching for exists in the tree, we don't have to check that it exists. We only need to use the letters. Okay, so we only need to use the branching letters. We only need to use the letters that lead us to the point where the string is, right? So we already know it's there. We don't have to make sure it's there. We know it's there. We only have to move to the position. Okay, I hope this helps. Okay, right? So that's why we can do skip count. That's why you can skip the C, right? It might not be immediately clear why we could skip the C. All right, so okay, so we have this piece of code, right? So it's we want to prove that this algorithm is linear in S2, right? So we want to prove that this takes only size of S2 time, okay? So the best way we have to do that is to use a potential function, right? And this is one of those for now, it's one of those easy potential functions. It's going to be a bit harder, but for now is one of those easy potential functions. So what should I use as a potential function here for this algorithm? It's a linear potential function. It's just one of the level, yes, exactly the level, right? So what do we mean by level, right? So whenever you have a point, wait, okay, so maybe on the skip count trick, it's easier. So whenever you have a point like this over here, there are two depths that we might consider. One of them is the tree depth, okay, which is the number of nodes that are above this point. Okay, so the tree depth of this point would be 3, right? And there is also the string depth. Okay, so the string depth is essentially the size of the path level, right? So this is what we called here the size of the path level. Okay, so the size of the path level of P or string depth. We can also call this string depth or string depth. Okay, so that's what Gusfield calls this, string depth. Okay, so it's the number of letters that exist from the root up to the position where we are at right now. Okay, so that's what we're going to use for our first potential function, right? So let's assume that our potential function is use phi of the data structure, okay, equals this thing, right? So we can call it string depth, size of the path level, so on and so forth. Okay, so let's call it string depth. String depth, right? So that's what we have for our potential function. Okay, so now we can go here, and what do we figure out? So in this easy case, right? So this line over here, so where I use the suffix jump, what's my amortized cost for this operation, right? And then for the whole cycle, right? So let's do one at a time. Okay. Okay, so let's do, what's the amortized cost of the suffix jump? Right? So it's actually the real cost. Okay, we actually know that the real cost is really complicated, right? But we're ignoring that because we're still in the first analysis, which is incomplete. So I'm just going to say that this is 1. Okay. So this is the incomplete analysis. So I'm just going to assume it's 1, right? But then what happens? We have the string depth of the point after, right? So after, and the string depth of the point before. Okay. So how does the string depth of the point changes when I do a suffix jump? So what happens to the number of letters that I have?
Decreases by 1.
Decrease by 1, right? So basically this delta is -1. Okay, so we're good here because our suffix jump, which was kind of complicated, now amortized to 0. Okay, so that's okay. So let's see if we can amortize the while cycle. Okay, so let's try to amortize this while cycle. Okay. Okay, so what happens for that while cycle? So basically for that while cycle, we need the real costs. Okay, and then we need the size of the potential function after and minus before. Right, so that's okay. So the while cycle runs a couple of times. So basically, let's assume that one of the times it fails. So this is when it's possible to descend. Okay, and this is when it's not possible. Okay, so it followed k suffix links. Okay, so if it followed k suffix links, then what happened? So what happened to this? So if I used k suffix link, what happened to the number of letters?
It got k letters shorter.
It got k letters shorter, right? So if we do this, we get that the amortized time of the while cycle is 1, right? And that basically means that we're golden here because we have a for cycle, and everything inside the for cycle is amortized constant. Okay, so this basically means that then the amortized time of the algorithm. Okay, this is just going to be just sum up all the amortized costs, right? So okay, so this is size of S2, right? So right, so we need to sum up amortized costs. We need to sum some other amortized costs. So we need to sum the amortized cost of the while cycle, and we also need to sum the amortized costs of descent. Okay, but let's assume that okay, we know how much the amortized cost of descent is going to be. So it's going to be the amortized cost of the while plus the amortized cost of the descent. Right, so this is basically what it's going to be. Plus, you can add a linear amount for the checking here. For this checking, you can add for a linear amount, but that's okay, right? So let's just put one more here, like for card checking for card checks. Okay, you can add this stuff. You don't need to, but it's okay. Right. So we saw that the while cycle is constant. It amortizes to 1. Okay, the descent is exactly the opposite of the suffix jump, right? So the descent also also needs one operation, and instead of decreasing the string depth, it actually increases. Okay, so you can basically say here that the amortized cost of the descent is 2, right? So, but that's usual, right? So basically, we took credits from the descent to pay for the suffix jumps. Okay, so here, this is going to be summing up from 1 to S2. The while cycle just adds to 1, okay? The descent adds to 2, and the while guard adds to 1. So this is like 4 S2, which is basically linear on S2. Okay, this would be great if it was a correct analysis. The problem is that it's incomplete, right? So it's promising if we're able to do the skip count trick in constant time, right? So now we need to do the complete analysis, right? So okay, now for the complete analysis. Right. Okay, so now we need to analyze suffix jump. right? So you need to analyze the suffix term. Right, so let's look at the suffix term. So what happens here? So when we're using the skip count trick, right? So this is not constant, right? Because, okay, so here it's, on this side it's constant. I always go to the parent, I always follow the suffix link. That's always the same, right? But here I might need to check a couple of letters, several letters, okay? So ideally, I would want to amortize this to constant, okay? Because if I'm able to amortize this to constant, then the previous analyses would be correct. The problem is, which potential function should I use for this particular algorithm, right? So for this stuff, what should I use as a potential function?
Something related to the distance to the father node.
Okay, that's actually, yes, that's true. But the distance to the, yes, that would actually work. Yeah, that would work fine. I think it's a bit, no, that would be fine. And yeah, that would be fine. Okay, that would work, right? So it could be the 4 here, right? So the distance to the father node. Yes, that works, right? That's a great potential function. Yes, that works, right? So we can use the distance to the father node. Instead, I'm just going to use something that's similar. Okay, that might be simpler to explain. It's not clear that it's simpler to explain, but okay, that would work. So what your colleague is saying is these 4 letters over here, they could have a variable which is the string depth between the point and the father node, or basically the difference between the string depth of the point and the string depth of the father node. Okay, you could have that difference. Instead, I'm going to use something else, okay, which is the following, right? So ideally what happens is that when you need to use potential, right? So when you need to use credits, your potential function should decrease. Now, if you look here from the point in this position and the point in this position, the string depth does decrease, but it doesn't decrease enough because the string depth decreases by 1 and I actually need 3 credits, okay? But there's another thing that we can define, which is the tree depth, okay? So remember that I used the tree depth, okay? I'll just call it TP, okay? Tree depth of P, okay? Okay, the problem is that when I go from this point to that point, the tree depth doesn't decrease. On the contrary, it increases, right? Okay, it's a very good point. So why am I not using, okay, so your colleague was saying that I could use these 4 letters over here, right? So basically the number of letters. But to be more precise, that's what, it would be correct, it would work. But to be more precise, the number of credits that I need is related to the tree depth, right? So when I go from here to there, okay, the tree depth increases by 2, right? So the number of credits that I need is 3. Okay, so it's 1 minus the number of credits that I need, but it would give me the credits that I need. The problem is that the tree depth is increasing and I was expecting my potential function to decrease. So what should I do? So what should I do? Right, so everybody got the problem. So if I'm using tree depth as my potential function, when I do this particular transition over here,
we negate it.
Sorry?
Can we negate the
tree? Yeah, we can negate it, right? So you just use a negative sign here. Okay, that means that this tree depth will actually violate a couple of the principles that we have for potential functions, which is they shouldn't be negative. Otherwise, we need to use the general equation. Okay. But minus the tree depth would be a good potential function for the skip config, right? Okay. Right. So basically, we can go here. Right. So, sorry. Tree depth.
Professor, sorry, I don't understand why the tree depth increases after we do the skip jump trick. Shouldn't it decrease by 1?
It decreases by 1, but it increases by 2. Right? Okay, so you lose one letter, right? So you lose the letter C. If there was a node here, then you lost that node. That's true. But you gain these two. Right?
Oh, I see. Okay. Okay, thank you.
You gain those. Actually, you can gain more, right? So because stuff like this, so here's your alpha 1. You can get a node here that splits your alpha 1 into 2 parts, right? So you can gain more nodes, but you don't know that, right? That might happen or not. But we know for sure that you gain these 2 down here, right? And that would be enough. Okay. Okay, but it's true. You might also lose one node over there, right? So that's a problem with using the. That's the problem with using the tree depth, right? Okay, but the thing is, we don't need a potential function only for the skip config. We need a potential function also to amortize the while, and that basically gives us, for our complete analysis, which potential function should we use, and the solution is we basically combine these two, right? So I need this one and I need the other one, right? So I need the string depth and I need to subtract the tree depth. Okay, and this potential function doesn't actually work because if you're in a situation like this one over here, like if you're in this tree, and suppose that your point is like this one, okay, here the string depth and the tree depth is the same, right? That means that your potential here is 0, okay? Which is not so bad because you're at the nodes, but in general, it might not be enough, right? So in this case, it's 0, and in this case, it's not so bad, but it could be 0, and it actually could be bad, right? So basically, the easy way to solve this is to just use a 2 over here, right? Okay. So you can use this potential function, right? Okay, so this is our potential function for analyzing this algorithm over here, right? So the algorithm for the longest common substrate. Okay, so all right. So basically, all you have to do is you need to check. You only need to check that the amortized cost of the suffix jump, right, really is 0. Okay, or yeah, or 1. Okay, if it's 1, yeah, sorry, you can if you check that the amortized cost of the suffix jump is 1, okay, because we assume that in this analysis, okay, then everything should carry through. Okay, so in general we conclude so ... and the longest common substring algorithm really takes linear time. Okay. Right. So in the next classes, we are actually going to see that this algorithm is the same algorithm that we use to build suffix trees. This is actually the algorithm that builds suffix trees. We only need to be mindful of how to represent them. But this algorithm that we build for this application is actually the algorithm that we do use for building suffix trees, right?